Good morning. Myself Nancy from Basic Chemistry Honors first year making the video on structure and bonding. Introduction. The property of the organic compound can be considered to their structure. In the another word, the structure of organic compound help us to understand the chemistry. By the structure, we can how the various type of atom in a molecule are linked together and what are their relative ordinate in the space. The organic compound essentially contain the carbon, hydrogen, oxygenally heteroatoms such as oxygen, nitrogen, sulfur, potassium, and hexone, halogen may be are also permanent. The various type of atom in the organic molecule are held together by covalent bond, and there may be a single, double, triple bond. In addition, these covalent bond each other are straight chain, and or the ring of these various size may be either hollow homocyclic, heterocyclic, and each can of them may be either be acyclic or aromatic. A covalent bond is formed by overlapping of the orbital, and the carbon atom does not use the pure atomic orbital, but the use of hybrid orbital for the forming this covalent bond. In the another word, we can discuss in the detail the different type of hybridization in the organic compound. Besides which, this we shall be also discuss about the different type of covalent bond and their effect on the property of the organic molecule. Hybridization. The ground state of electronic configuration of the carbon is since the ground state of the carbon does not fill half-filled atomic orbital, and therefore it should be only two covalent bond. It should be divalent, but the compound of CH4, CCl4, C2H6, etc. The carbon have the four bond and hence the tetracovalent. Now the question rise why the carbon formed the four covalent bond. It had two half-filled orbitals. To answer this question, let us compare the atomic amount of energy released by the CH2 and CH4. We can discuss that a typical CH bond is about 418 Kelvin 0 mole inverse, and the reaction will be with the hydrogen atom form the CH2 such as liberate the axis C8C 3k kilojoule of an energy. Alternative, if the carbon atom is to form the four bond, it can have the four half-filled orbital. This is possible if we can assume to that one of the atom of these orbital is unpaired and is promoted to the vacant 2p orbital, and such, and therefore this electron configuration of the carbon is first in the excited state. The proportion of the energy required of 401 kilojoule of the energy, but the energy is more than the competitive by the formation of two additional bonds are discussed below. In thus, it is clear from formation of CH4 is about 1272836 is equal to 4835 kilojoule per mole. The thermodynamically more favorable for than the formation of CH2. This is because the reason that the carbon always showed the tetracovalency. Now, the exit state of the carbon has been half-filled orbital. One is of 2s and 3 in the sp, and hence can be overlapped by the 1s orbital of hydrogen atom to form the 4 CH bonds. Since the 2s orbital is spherical in shape and the sp orbital is dimpled shape, and I include underline at the angle of 90 degree to one another. Therefore, CH bond formed by the overlap of two s orbital and can we have the one s orbital hydrogen should be different from the other three CH bond which are formed by overlap of the two s orbital of the carbon with the 1s orbital of hydrogen atom, but the electron, neutron, and diffraction studies has been related that all the four bonds in the methane are equivalent to all repeats. All this bond strand of 43k kilojoule mole inverse the bond length of the 110 picometer and are directed toward the four corner of the regular tetrahedron. To explain this fact, the concept of hybridization was introduced, and the hybridization may be defined as a phenomenon of mixing bleeding of bond length 1010 picometer, and these are discussed toward the four corner of the regular tetrahedron. To explain this fact, the concept of hybridization was introduced, and it was a phenomenon of mixing the two or more atomic orbitals exponentially equal energy of the atom to the form an equal number of new orbitals have the equal energy and identical shape and size, and this and are structurally symmetrically ordinated in the space. These new orbital tucks formed is called hybridized orbital. How does the carbon undergo the hybridization? The concept of a hybridization explains how the carbon atom formed the four equivalent tetrahedral bond, but it does not answer why do it so. To answer this question, let us examine the shape of the atomic orbital that mix and the hybrid of the orbital that result. The shape is of the hybridized orbital, and the mixture of the s and p orbital is like that p orbital, except that two lobes are equal as shown in figure 1.1. The larger lobe of the participate is in the bond formation while the smaller lobe does not. Since the size of the large lobe is always bigger than the individual sp orbital taking part in the hybridization, hybrid orbitals are always stronger bond, and it is because of this reason that the carbon always undergo the hybridization period to bond formation. Type of hybridization depend upon the number and the type of orbital merged together. The carbon undergo the following three type of hybridization. First is sp3 or tetrahedral hybridization. As stated above, in this type of hybridization, 1s and 3p orbital are to form the four equivalent hybrid orbital. Since there are the four hybrid orbital are directed toward the corner of a regular tetrahedron, and therefore this type of hybridization is also called tetrahedral hybridization. All saturated compound of the carbon such as alkene, cycloalkene involve the sp3 hybridization. First step of the methane molecule. In the CH4 molecule, there is a sp3 hybridization. Each of these form the sp3 hybrid orbital, then overlap the 1s and to form the H atom to form the 4 sp3 as CH and pi bond as shown in the figure 1.2. The methane is a tetrahedral molecule with each CH bond angle of 109 degree 28. All these have the 4 CH bond are equivalent and are 110 picometer long, and each the carbon atom has a bond dissociation energy of 416 kilojoule per mole. Second is shape of ethane molecule. Like the methane, in the ethane molecule, each both the carbon atom are the sp3 hybridization. In another word, each carbon atom have the four sp3 hybrid orbital inclined to one another at the angle of 109. One of these sp3 hybridization of the carbon atom overlap the sp3 orbital of one other carbon atom with an internuclear axis forming a sp3 and C carbon-carbon single bond and pi bond. The remaining three sp3 orbital on each carbon atom with the 1s orbital have the three hydrogen bond along their intermolecular axis, forming the all six sp3s and pi bond. The complete orbital mixture of the ethane is shown in figure 1.3. Since each carbon of the ethane have sp3 hybridization, therefore the ethane, like the methane, is tetrahedral molecule, and their bond parameter of the ethane are also as shown in figure. First is carbon-carbon single bond length is equal to 154 picometer. Second is each carbon hydrogen bond length is equal to 110 picometer. Third is each carbon or carbon hydrogen bond angle is 109 degrees Celsius, and the fourth is carbon carbon dissociation is 347 kilojoule per mole, and each carbon hydrogen bond energy is 409.6 kilojoule per mole. Second is sp2 or tetrahedral hybridization. In this type of hybridization, one s and two p orbital combine to form the three equivalent sp3 orbital, while the third sp orbital remain unhybrid. These sp2 orbital lie in a plane and the directed toward the three corner or equivalent triangle. That is why the sp2 hybridization is always called tetragonal hybridization, and the unhybridized spz orbital is however perpendicular to the plane containing these three sp orbital, or the compound of a carbon containing the carbon-carbon double bond, such as alkane, arenes, and the involved sp2 hybridization. The shape of the ethane and ethine molecule. In the ethine molecule, each carbon is of sp2 hybridized. Now, one of the three sp2 hybridized orbital of each carbon overlap naturally among their intermolecular nuclear axes to form the sp2 carbon-carbon and pi bond. The remaining two sp2 hybridization of each carbon overlap with the one s orbital of the carbon atom to form all four sp2s and the carbon, hydrogen, and pi bond. Further, since all these three type of sp2 orbital of these carbon lie in a plane, two carbon atom and the four hydrogen atom are also lie in a plane. Each carbon atom is now left with a one unhybridized spz orbital, which is perpendicular to the plane of the carbon hydrogen atom. These are the two spz orbital are parallel and hence have overlap sideway to form a pi bond. Thus, the pi bond is perpendicular to the plane of carbon and the hydrogen atom, and further, the electron cloud of the pi bond consists of two equal halves, one lying above and another lying below this plane. From the above discussion, it is followed that the carbon-carbon double bond consists of two different type of bond, the pi bond and the sigma bond. Whereas the sigma bond is symmetrical along with the carbon and the pi bond is thus not. However, the pi bond is bisect by the plane of containing two carbon atom and four hydrogen atom. The bond energy of the carbon-carbon single bond and carbon-carbon double bond can be determined to be 347 kJ per mole and 598 kJ per mole respectively, give a bond energy of to the pi bond. The pi bond is weaker bond and than the sigma bond, and there the weaker of the pi bond easily break the chemical reaction, for the pi bond can be responsible for the chemical reactivity of the ethane and the other alkenes. A carbon-carbon double bond is shorter as compared to the carbon-carbon single bond length, and this is due to the fact that the sp2 hybridized is smaller in size than the sp3 hybridized orbital. Furthermore, the sideway overlap of the p orbital are bring the two carbon atom little closer to have a maximum degree of overlap. Third is sp or diagonal hybridization. In this type of hybridization, the s and p orbital combine to form the two equivalent orbital, while the remaining two sp orbital remain unhybridized. The two sp orbital are inclined to each other at an angle of 180 degree, and this is why this hybridization is also called diagonal hybridization. The two unhybridized orbital and however perpendicular to each other and also to the two sp or hybridized orbital. The shape of acetylene or ethylene molecule. In the acetylene molecule, each carbon atom is sp hybridized, and a hybridized carbon has the two sp or hybrid orbital, and the sp orbital of each carbon overlap with each other to form the ssp, and the second sp orbital overlap to the first orbital of hydrogen to form the sps carbon hydrogen pi bond, and therefore the sp orbital of the each atom belong to a straight line, and overlap take place along with the intermolecular axis, and therefore all this atom of acetylene line along with the straight line, and thus acetylene is a linear, and each of the atom is now left to be two unhybridized spy and spz orbital, and these are perpendicular to each other and also to the plane of the carbon and the hydrogen atom. Two spy orbital of one of the each carbon atom overlap sideway to form a pi pi bond, and similarly overlap between the sp-z orbital one to another carbon atom result in formation of the second pi bond. As a result, as shown in figure 1. A. Since the p orbital has two lobes and this carbon atom of the pi bond has two halves, and if the two halves of the one pi bond are considered to be lie and below the line, the joining of the two carbon atom, then the two halves of the second pi bond will lie at the back of this line. However, the half of the electron could be have two pi bond and do not stay as but merge together to form a single cloud, and therefore this cylindrical symmetry about the intermolecular axis. From the above discussion, it is followed that the carbon-carbon triple bond is made up of one strong pi bond and two weaker pi bond, and the total strength is 803.3 kJ per mole as compared to the 598 kJ per mole for the carbon-carbon double bond is ethane, and 348 kJ per mole for the carbon-carbon single bond in the ethane. Due to the smaller size of sp orbital and the sideway overlap of the hybridized p orbital, the carbon-carbon bond distance in the acetylene is only of 120 picometer, and since the acetylene molecule is linear and therefore the hydrogen carbon bond is of 180. The bond length, we know that during the duration of the formation of chemical bond, the combined atom approach each other. As they come closer and closer, the potential energy of the system keep on decreases until at a certain minimum distance between the two atoms, the potential energy of the system become minimum, and the attractive repulsive force or just balance each other, and the minimum distance between the center of the nuclei of the two bond atom at which the attractive and the repulsive force just balance each other and the potential energy of the system become minimum is called bond length. It should be noticed that because of the constant vibration of the bond atom, the distance does not remain constant. In fact, the bond length is actually average distance between the nuclei of the bond atom is expressed either in the angstrom unit or the pico unit and can be determined with the help of physical methods such as X-ray diffraction, neutron diffraction, and spectroscopic method. The method of the bond length between the two atoms XY remaining constant is independent of the natural molecule of food classes of the compound. For example, CH bond distance remain to be 110 picometer in a large number of the saturated compounds such as methane, ethane, propane. The bond length of some of the typical bonds are listed in the table 1.1. The magnitude of the bond length depend upon the flowing factor. First is size of the atom. As the size of the atom increases, the bond length increases in the same order. And for example, as the size of halogen atom increases, the bond length of the carbon halogen bond increases. Multiplicity of the bond. As the multiplicity of the bond between the two atoms increases, the bond length decreases, and therefore carbon-carbon bond length is 1.54 nanometer. That of carbon double bond is 1.37 nanometer, and that of carbon triple bond is 1.20. Type of hybridization. The p orbital is much bigger in the size than the s orbital of the same shell. Therefore, as we go from the sp to sp3 to sp2 and then to sp, the percentage of the p character decrease from 75 to 60, 66.7, and from to 50 according to the size of orbital decrease in the same order, where sp3, sp2, and sp is bigger size from a longer bond, and therefore carbon single bond length decrease in the order. Further, since the sideway overlap of the two p orbital bring the two carbon atom closer to a heavy and optimum degree of overlap, therefore a single bond is longer than double bond, which is turned in a longer than a triple bond and tucks. Similarly, a carbon-hydrogen bond may be formed by the overlap of sp3, sp2, and the sp orbital of the carbon atom with an sp orbital of hydrogen, and therefore, as the size of hybrid orbital decreases, the length of the carbon-hydrogen bond decreases accordingly. Bond angle. A polymer Polyatomic molecule contain more than one covalent bond. Each covalent bond in turn is formed by the overlap of the atom and or the hybridized orbital, and since the atomic orbital and hybridized orbital are directed in nature, and therefore the covalent bond make the angle between them. Thus, the bond angle between the two adjacent covalent bonds in a polyvalent molecule is called the bond angle. Like the bond length, the bond angle is measured by the X-ray diffraction spectroscopy method. This is because of the constant atomic vibration, and the bond length thus measured as are actually average bond angle. In the journal, the bond angle depends upon first on hybridization, second the number shared, and the lone pair of the electron around the center atom in a molecule. Since the magnitude of the repulsion between these three pairs decrease in order, the lone pair therefore, as the number of lone pair increases, the titration and regular saturated geometry occur and the bond angle decreases from their accepted value. For example, the methane, ammonia, water, and the central structure of the carbon, nitrogen, oxygen of all three types of hybridized, and therefore all these molecules are accepted to be tetrahedral with the bond angle of 10928. However, the geometry and the bond angle are different as shown below. Since the lone pair bond pair repulsion is greater than the pair bond pair repulsion, and therefore the angle decreases from 109 degree in the CH4 to the 107 degree in NH3. Further, since the lone pair repulsion is even more severe than the lone pair bond pair repulsion, therefore the bond angle further decreases from 107 in the NH3 to the 104 degree in NH2O. Thus, the evidence from the above discussion that the bond angle of the sp3 hybridization carbon atom bond will be always tetrahedral, and only for all the atoms are grouped attached to it are identical as in methane and neopentane and the carbon tetrachloride, etc. In all these cases, the angle derivation is a little from the tetrahedral value. For example, carbon and bromine bond is 2 bromopropane in the 144.2 degree, and similarly the variation are generally found from the identical value of the 120 to 180 of sp2 and sp orbital respectively. For example, the 160.6 respectively. This is due to the reason that the pi bond bring less tightly held by the carbon accepted the repel bond of the carbon hydrogen bond more than the carbon bond pair of the carbon hydrogen bond accept each other. Bond energy. When a covalent bond is formed, some amount of energy is always released, and conversely, the amount of energy will be supplied to break the bond. The amount of energy repelled to break the 1 mole of the bond, two atoms are called bond dissociation energy, and this is a symbol of D and expressed in kilojoule per mole. For example, 435 kilojoule is required to break 1 mole of the hydrogen molecule in a individual atom, and this bond dissociation energy of hydrogen is 435 kilojoule per mole. In fact, the bond dissociation energy is measured of the strength of the bond, and usually greater the bond dissociation energy, greater is the strength of the bond, and the bond dissociation energy of the atom of divalent atom are given in table 1.2. However, in the case of polyvalent atom, the bond energy may be different meaning. First is bond dissociation, which is the energy required to break the 1 mole of the particular bond, and the bond energy, which is in the average of different bond dissociation for all the similar bond present in the molecule. The symbol of is by the E, and let us now exclude that the difference between the two atoms term by considering the, for example, the methane molecule. If the mean to be removed from the 4 hydrogen atom at one time to by breaking the CH bond, and we will be have the 4 different type of value of the bond dissociation energy. The question which arises now is why do get the 4 different type of the bond dissociation energy when we can break the carbon hydrogen bond in each step. This is due to the reason that the bond energy does not exclude the bond energy required to break a particular bond, but also exclude the bond energy change, which is accumulate the process of hybridization of the carbon atom, which is different from each step, and the directed converting the methane into the carbon hydrogen atom required the 1665 kilojoule per mole inverse of the energy, which is actually the sum of 4 bond dissociation degree listed above. The evidence of the average bond association energy per mole of the carbon hydrogen bond in the methane is equal to 146.25 kilojoule per mole inverse. In general, the bond dissociation energy depends upon the fact that first the size of the atom, as the size of the atom forming the covalent bond increases, the greater will be the size of bond and hence smaller will be the bond energy. For example, the bond energy of the carbon halogen bond decreases from CF to the I in the size of halogen decreases from the F to I. Multiplicity of the bond. As the multiplicity of the bond increases, the bond length decreases as the hence the bond energy increases. For example, the C triple bond and C double bond have greater than the CN. Type of hybridization. As the percentage of sp increases from the sp2 and sp, the size of the hybrid orbital decreases as a result of bond length decrease and hence the bond energy increases. For example, in contrast to the pi bond, there will be a side overlap of the p orbital and extend to be the overlap the side way are low. A carbon pi bond is always weaker than the carbon carbon sigma bond, and therefore the carbon carbon double bond is stronger than the carbon single bond, and this is include the sigma bond and weaker pi bond. In a similar way that the carbon atom is triple is stronger and then the carbon carbon double bond locality and delocalized localized bond. A covalent bond is formed by the overlap of the atom and the hybridized orbital. The electron which form these bonds can either be localized or delocalized. If the electron form covalent bonds spend most of their time in between the space of two particular atoms, such electrons are called the localized atom, and the bond formed by these atoms are called localizing bond. In contrast, if the electron forming a covalent bond are not confined to the space between these two bonding atoms, the electron is called delocalized and Tux form is called delocalized bond. Since the electron form whole type of sigma bond as in figure and bond of the methane, bond in ethylene, bond in acetylene are localized between their respectively participation atom. These are called localized electron and the bond formed by these are called localized bond and exclude the type of sigma bond or localized bond, and in contrast to the electron forming pi bond may be not be localized. For example, the electron forming the pi bond in a line confined the space above and below the carbon carbon pi bond. Therefore, the sigma bond pi bond of the ethylene is localized, and therefore the electron pair forming the pi bond are also localized. And however, the two pi bond of acetylene delocalized. Hence, the electron of the pi bond in the plane of the paper do not remain confined to their region above and below the carbon carbon sigma bond are similar, and the electron forming the pi bond are in the plane perpendicular to the paper and do not remain confined to the region to front and back of the pi bond, and therefore these have the half of the electron cloud mirrors to one of the cloud, and which of the four pi bond and two pi bond in this line are also localized. Further excluding benzene. Each carbon in the benzene in sp2 hybridization. Each carbon have the sp2 hybridized orbital and one unhybridized 2pz orbital. The sigma bond of bond skeleton of the benzene is formed by overlap of two sp2 orbital of each carbon with the similar orbital of the carbon atom and one sp2 hybridized orbital of each carbon with the one s orbital of the hydrogen as shown in figure 1.8. The electron of these pi bond are localized in a region between the participation atom and hence called older pi atom and localized bond. Each carbon is shown now left on which the hybridization of p orbital. The six orbital of the p orbital have one the electron each and not to the all are parallel to one another but the perpendicular to the plane of the pi sigma bond and carbon skeleton. And another two p orbital are adjacent carbon atom and closer enough for a sideway overlap of the pi bond. Now these are the two equal good way in which the p orbital is adjacent carbon atom and can be overlapped to form 3 pi bond as shown in figure 1.2. 1.9 A and B. In fact, the 2p orbital overlap equally with the 2p orbital on adjacent carbon atom on the one side, another side to the two dot nut shaped sigma bond cloud, one of which have above and one of the below of the carbon atom. Hydrogen atom in the shown in figure 1.10. Thus, the p orbital can be confined to the simple pi bond between two carbon atoms was be case between the two structures as figured in the 1.9. But the involving information of more than pi bond and the 6 pi bond are be completely decolorized in all these carbon atom, and the ring, in another word the 3 pi bond of the benzene are completely decolorized, and therefore it is not present the benzene with the help of the hexagonal ring. The 3 double bond is alternative position, and since these positions of the pi bond are not fixed, and therefore the benzene is the best representative of hexagonal ring with a circular inside the ring, and this denote the 6 complete decolorized pi bond. Effect of decolorized bond. The two important characteristics of decolorized bond are: first is effect of carbon-carbon bond length. The continuous structure of the benzene ring have the 3 carbon and the 3 double carbon bond, and this alternative position. Therefore, this explains the bond length of the 154 to 134 picometer respectively. Due to the complete decolorization of the sigma are called equal attached by the all the six carbon atom. As a result of the carbon bond equal to 139 pm and lie in the between of carbon single bond and carbon double bond length. Similarly, due to the overlap between the p orbital, the C2 and the C3 have the atom of 1,3-butyl molecule, and 3 and 2 bond has a same double bond characteristic. As a result of C2 and C3, when bond length decreases from the accepted value of 154 to 149 pm picometer, and the effect of stability due to the decolorization of pi bond greater to the area the pi electron density on the each atom decreases. As a result, the energy system decreases and its stability increases. The extent of this stability is however measured in terms of resonance energy and decolorization energy. Observably higher the resonance energy, more is stability. An example of benzene with resonance energy of the 154 is much more stable than the 1,3 with the resonance just as in the 16.2 kilojoule per mole. Van der Waals interaction. As we have known that the gas does not obey the ideal gas equation, and the second is non-polar as shown in the neon argon N2O2, and can be considered the first to be liquid and then to the solid state. In order to account this observation, the van der Waals district chemist possessed the existence of the some sort of alternative force between the forces of the non-polar compound. He named these forces as a van der Waals force of attraction. These forces operate only a small distance and result for formation of induced polarization of the electron cloud in the molecule, as is discussed below. The normal in the non-polar molecule, the center of the negative positive charge and still consist with each other, and hence the molecule do not have any dipole moment. However, because of the good constant random movement of the electron and the cloud, the nucleus is accepted that at the instant of the time these closer atoms can may be slightly discordant, and due to the collision of these molecules or by some other factor, the constant at the instant of the time, the center of the positive and negative charges still do not cross a temporary dipole moment is induced in one of the molecule, and the temporary dipole moment in the one molecule cause an early molecule or the temporary positive dipole moment as a small attraction is induced in the molecule. The induced dipole attraction are called London force or and dispersive forces. Also, these are the temporary dipole which have only translatory exist constantly between the combined effect of the larger number of the attractive forces significant is reflected with their property. The force is weaker and the maximum solid is minimum in a gas due to the difference in the intermolecular distance in the two cases. In another word, these are the short range forces operate only by those portions of the molecule which touch each other between the surface of the molecule. Evidence: the greater the surface area of the molecule, stronger are the van der Waals force of attraction. With the help of explanation of the effect of molecular size, shape of the physical property of any of many substances. For example, the boiling point of the N alkane show a regular increase in CH2 group as we have this assigned to the homologous series. This is due to the reason that the molecular force of mass of the alkane increases and the molecular size and the surface area of also increase accordingly. As a result of this magnitude, the van der Waals force of attraction increases and hence the boiling point of an alkane increases as the molecular mass increases. Almost the isomer the branching chain may be inversely and the boiling point then the corresponding alkane. This is due to the reason that the branching of the shape of the molecule tend to approach and that of the sphere. As a result of this surface area of the branching, the isomer decrease and due to the lesser surface area of the molecule, the van der Waals force of attraction operate between these molecules become constantly smaller and hence lesser amount of energy is required to over them. As a result of the boiling point, the branch of the chain are lower than those of the corresponding alkane, and further it can be observed that greater the branching, lower is the boiling point. For example, the van der Waals, as discussed in the magnitude of the van der Waals of the attraction increases as the distance between the two molecules and non-bonded atom decreases, and this is the attraction is maximum when the molecule and non-bonded atom are minimum distance touching each other. If they are forced to closer than that of minimum distance, then the alternative force turn into the repulsive force of the van der Waals, and this localized to the state that every atom of the molecule have an effective size and the van der Waals force of the radius. If the size of the van der Waals force radius have two non-bonded atom of the molecule, it can then the distance between them and then the alternative force turn to into the repulsive force. And for example, consider the boat of the cyclohexane. The distance between two flap pole hydrogen is just 183 picometer, and which is lesser than of the van der Waals radius of the two hydrogen atom, and hence the boat form of the cyclohexane is less stable than the chair form in which non-repulsive exists. Similar to the cis-1,3-dimethyl cyclohexane is more stable when the atoms of the methyl group are non-equivalent or ornamentation, then they have an axial orientation. This may be explained as a follow, in which the diaxial configuration and the distance between two axial methyl group of C1 and C3 is lesser than that of the sum of the van der Waals force, and similarly the distance between diaxial methyl of the C1 and diaxial hydrogen of C3 is lesser than that of the sum of the van der Waals force radius. As a result of repulsive force, or this set of the repulsive force is called 1,3 diaxial interaction and simply steric strain. However, in the equatorial configuration, the two methyl groups are held at a distance more than the sum of these van der Waals radius, and hence such name of the repulsive force do not exist. As a result of equatorial configuration of cis-1,3-dimethyl cyclohexane is more stable than the diaxial configuration of cis-1,3-dimethyl cyclohexane. Type of van der Waals forces. This day I will discuss that van der Waals force of attraction is induced between dipole-dipole interaction occurred by the non-polar molecule. However, in the the polar molecule, the van der Waals force of attraction may be originated in dipole and dipole-induced dipole attraction are induced. The first is dipole-dipole interaction. In the case of the polar molecule, the van der Waals force of mainly is due to the electrical interaction between the opposite charges and the molecule called the dipole-dipole interaction. For example, the gases such as NH3, SO2, HCl, HF has a permanent dipole moment, as a result of which there is a dipole-dipole attraction between the molecules in these gases, and this magnitude of this dipole attraction depend upon the dipole moment of the molecule concentration. Evidence greater the dipole moment, stronger is the dipole-dipole interaction. Because of these alternative force, these gases can be easily liquefied. Dipole-induced dipole interaction. A polar molecule may be sometimes polarized. Is a non-polar molecule which lie in the intensity and induce the polarity in a neutral pieces of the iron lie closer by it. Induced dipole and then interact with the dipole moment of the first molecule, and therefore the two molecules are alterate together. The magnitude of the interaction is depend upon the magnitude of the dipole moment of the polar molecule and the polarity of the non-polar molecule, and the solubility of the inert gas is H2O increase with the H2 Rn due to the corresponding increase in magnitude of dipole moment. Dipole insert gas as in the H2O increases from helium to Rn, and it's due to the corresponding increase in magnitude of dipole induced dipole interaction as the polarity of the normal gases increase with increase in size from the He to the Rn. Excluding excluding compound and the collecting trace. The certain organic compound such as urea, ferric, hydroquinone are defined as a crystalline shape, and however in some cases the crystalline shape of these compound undergo change in the presence of the certain other compound. The former compound which are crystalline structure change into the called the host, and while the other later one are those who present change the crystal structure of the former compound are called gas, and the crystal of these compound have a space large enough to count the molecule of the greater gas compound. There is an There is no chemical bonding between the host and the gas, and these also alternative force of the weaker wonder force of interaction type of the host gas addition compound depend upon the shape of the space available within the crystal lattice. The host molecule, the host gas addition are of two types. First is enclosing compound. These are the space available within the crystal and host molecule in the form of long channel and the channel, and the host gas addition are also called the exclusion compound. The calatharis indissoluble between the crystal lattice of the host molecule in the form of gas and the host gas addition compound are called the class Tharis, and both of the addition compound of the crystal solid, but they are not useful as a derivative since they are decomposed at the boiling point of the host compound alternative. These addition compound are different, but they have no one common feature to gas molecule, and only the right side and the shape are fitted in the crystal lattice in the molecule. Let us discuss these addition compound in the latest more detail. First is excluding compound. The most common host molecule for the excluding compound is urea. Ordinary crystal urea are tetrahedral shape. However, when the gas is present, the urea crystal in the hexagonal lattice in which the gas molecule are present in the long channel, and it may be noted that the hexagonal shape of the lattice is formed only when the gas molecule are present in the suggesting theory. Thereby, the van der Waals force of attraction between the host and the gas molecule is essential for the stability of the such type of compound. The diameter of the canal is about 5 mm, and which molecule can act as a gas center depend upon their shape, size, not on the electronic or chemical effect. And these example of octane 2-cyclooctane, 1,3-bromooctane, and are highly right size. Turks, Turks act as a gas of the urea, 2-bromooctane, 2-methyl heptone, and 2-methyl octane do not fit in the size channel in the urea, and hence no act as a gas of the urea lattice. Likewise, both the dibutyl malonic and dibutyl furet are the gas, but either the diethyl is on the non-diethyl furet is a greatest, and simple the dipronic furet is a greater known, but the polaric channel of these may be. For example, the octane urea ratio is 1:6.73. Further, it has been shown that the spectroscopic that including the compound urea molecule do not remain resistive between the 1,8 flip and about 3 carbon double bond oxygen rate to be more than 10 ki power 6 per second at 303 Kelvin. These complex are the solid but are not as a derivative, since the melting point melt between the decomposed the melting point of urea, and these urea are separated by the isomer which are otherwise difficult to separate. Example, the straight chain of the C6-octane as can be separated from its branch isomer and the 2-methyl cyclohexoctane from the exclusion compound with the help of 2-methyl heptane does not. And further, the urea excluding the complex has been used as a method for resolving the racemic mixture. Example 2-chloroprotein to the excluding the which can be separated by the crystallization. Like the urea, the triurea also form the exclusion complex of the channel of the large diameter, and consequently the N-alkane cannot be act as a gas. However, 2-bromoctane, cyclohexane, cyclochloroform are the right shape and the size to fit the channel in the triurea to form an exclusion complex. The other well example of including this charged iodine complex. The charge is a deep blue colorization of iodine. Such in fact have two compound amylose which is water soluble and amylopeptine which is insoluble in water. Amylose has a helical structure. Inside the helical it is just as a right size and the polarity to accept an iodophore molecule. Thus the blue color is due to the formation of inclusion complex between the amylose and the iodophore molecule as shown in figure 1.16. Second is Clasterius, the host gas addition compound in which a crystal lattice of the host has a case-like cavity called the crystallis or case compound. Unlikely than the exclusion compound, the crystal of this crystallis is particularly vacant, and the most important host of the crystallis compound are quinine, hydroquinine, water, sodium chloride, and some other alkyl metal halide. Depend upon the nature of the host catalyst, having the mainly divided into the following two category: quinol. In these categories, the hydroquinone act as an host, and three molecules of the hydroquinone held in by the hydrogen bond from a case of the cell world 4 mm diameter. This gas molecule fit into these activity, and normally all the activity are filled. And these type of gas of quinol cater are methanol, SO2, CO2, H2S, CH3, CN, and noble gases as argon, krypton, and xenon. We have excess solution of hydroquinone, the crystal under the pressure of 10 to 40 atmosphere of the argon, krypton, and xenon. As the gas get erupted in the crystal lattice of the hydroquinone to form a crystalline crystal with the composition compound to the 2 quinol 1 gas atom, and this crystal may be quite stable and can be preserved for the years. However, when we heat and dissolve in which water or any other solvent, and the hydrogen bond crystal of the lattice of hydroquinone break and the rapid normal gas escape, it can be noticed that the smaller the noble gas such as helium, neon do not form the crystal compound since the atom of these gases are too small to the entrapped. Second is water. The another important compound is water. Usually six molecule of the water form the case in which the gas molecule of the appropriate size and shape of Cl2, propene, methylide, the noble gases cannot be interrupted. Thus, when the water is formed under the high pressure of any above the noble gases, the solid crystalline compound of the formula 150.75 H2O ratio 1 gas atom are formed, and these are the crystalline compound but are not commonly called as a noble gas hydride. These are the noble kept at a low temperature because at the high temperature they decompose helium, neon, however do not form the crystallography, and since these atoms are too small to be interacted. The another inorganic host is NaCl, which can be interrupt the organic molecule like the benzene, naphthalene, and diphenylmethylene. The use of calotropous. The same important calotropous noble gases are listed below. Since the helium, neon do not form the calotropous, therefore the gases are separate from the other noble gases such as argon, krypton, xenon present in the mixture. Calotropous provide the efficient method to store the radioactive isotope chlorine produced in the nuclear reactor. Charge transfer complex. The molecule complex formed by the mixing of the two electron molecule called the donor molecule represent as the two electron power poor or the sufficient During the formation of this complex, the donor molecule of donate these non-bonded and the unshared pair of the electron as a pair of electron of double bond and aromatic system to accept the molecule, and such complex are also called electron donor acceptor complex or EDA complex. This formation of the charge transfer complex may be represented as follow. In the case in this complex, the binding force between the donor and the acceptor molecule are weaker complex force. These electron septa of the charge transfer complex is not same as those of the septa of the two individual molecule, and this property is used to test to find whether a charge transfer complex has been founded or not. Further, because of the energy of the first exist state of the complex is very closer to the ground state, there is usually absorption band in the visual or the near the UV region, and his EDA complex are usually colored, and one of the most often inverted charge transfer complex are periprate, which is discussed in detail before. Peric acid form the charge transfer complex from many aromatic hydrocarbons and the aromatic amines, alphabetic amines, phenol. These hydration compounds are called the pericates. And these are usually yellow, orange, red colored solid which are defined to be melting point and hence are often used to derivative to characterize the above cases compound. Beside the peric acid, 1,3,5 trinitrobenzene and many also the other polo nitro compound formed such type of hydration complex, and this formation of the periate is excluded by the rate between the peric acid and the mesethylene 1,3,5-trimethylbenzene. The determination of the crystal structure of period has been evolved that the aromatic rings are held in the parallel plane. This is brought to observation of that 3-methyl 2,2,4,4,6 pentnitrothdiphenyl in which the two aromatic rings cannot be extreme the copolarity because of the steric interference does not form a charge transfer complex. In a charge transfer complex discussed above, the electron density 135 trimethylbenzene is higher due to the plus I effect of the 3-methyl group and hence act as a donor, while as the electron density in the peric acid is low due to the minus and minus I effect and minus R effect of the 3-nitrobenzene, and hence is act as an acceptor. Observed the stability of the charge transfer complex would be increases or formation of charge transfer complex is facilitated by the presence of the electron donor group in the donor molecule. The electron withdrawing group is in an acceptor molecule. For example, the methylene with the 3 electron donating methyl group form a charge transfer complex with the peric acid and 1,3,5 trinitrobenzene, but the benzene does not have any electron donating group. Does not. During the formation of charge transfer complex, one molecule acts as an electron donor and the another electron acceptor has a low ionization potential, and A has a high electron affinity at low energy, and due to the parallel arrangement of the ring, the overlap occurs between these atoms result in transfer of the electron with the highest occupied pi electron orbitals at the low unoccupied molecule. These are further distance between the D and N molecule, and this suggests that there is the highest likely overlap of the pi electron. The ring alternative, this complex may be regarded as a resonance hybrid of two contributing structure held together by the van der Waals forces. Whatever may be the name of the alternative force of the bonding in a charge transfer complex is usually weak, and hence a complex radial dissociation in the solution extend the charge separation in the charge transfer complex is measured by a dipole moment, and this which is often higher than the acceptor molecule. For example, the dipole moment of pyridine is raised to be 4.9 dipole in the pyridine iodine complex. Similarly, the 1,3,5 trinitrobenzene does not display any dipole moment in the carbon tetrachloride but does not signify the dipole moment in the benzene due to the formation of charge transfer complex, inductive effect, and field effect. Whenever the electron withdrawing group act as the Cl is attached to the end of the carbon. These pi electron of the C and Cl bond are attended by the spread of the two more electropositive chlorine act as an to displacement. The Cl atom acquire a negative charge and the C1 acquire a positive charge as shown below. The smaller alternative charge of the C1 attract to the pi bond and C1 C2 have together themselves as a C2 has occupy a small positive charge, but the charge will be smaller than on the C1. And similarly on the C3 the positive charge will be smaller than the C2 and this effect is transferred further, but the intensity becomes decreasing with the distance, and this type of pi electron displacement along the saturated carbon atom due to the presence of a polar molecule bond is called inductive and I effect. This inductive effect is also transferred to beta T effect. The inductive effect is most powerful of the carbon atom to the heterocarbon atom is connected directly and dies off the quickly as the distance of the carbon atom from the hetero increases. In fact, the inductive effect is almost negligible behind two carbon atom for from the tetrahedro atom. Characteristic of inductive effect. First is inductive effect involve the only displacement of pi electron occur in the polar single covalent bond. Second is inductive effect is permanent effect and cannot be reversed. Third, the inductive effect decreases progressively as the distance between the carbon atom and the electron withdrawing group or the electron donating group or the group increases. Fourth is this displace the electron do not leave their orbital. Instead, only the later distortion of the orbital occur when they cause a polarization as shown below. Fifth, depend upon the electron donating or electron withdrawing ability. Different atom or the group cause the polarization of covalent bond of different existence. Application of inductive effect. Application first is stability of the reactive intermediate. The relative stability of the free radical carbocation carboanion can be explained on the basis of inductive effect. Second is polarity of the covalent bond and display dipole moment of the organic compound. Inductive effect cause polarization of covalent bond between two similar atoms. Due to this charge separation, each covalent bond has a defined dipole moment. The magnitude of this dipole moment, however, depend upon first is electronegativity difference between the two atoms forming the covalent bond, and second is origination of the various polar covalent bond in an organic compound as described before. First is electronegative difference. Greater the electronegative difference between the two atoms forming the covalent bond, more is the polar covalent, and hence greater is the dipole moment of the organic compound. For example, dipole moment of the flowing compound increase as electronegative difference between the carbon and the hydrogen increases.
The electronegativity difference between the two atoms forming the covalent bond and the orientation of the various polar covalent bonds in organic compounds as discussed below. Electronegativity difference. Greater the electronegativity difference between the two atoms forming the covalent bond, more polar is the covalent bond and hence greater is the dipole moment of the organic compound. For example, the dipole moment of the following compound increases the organic compound. For example, the dipole moment of the molecules is increases as electronegativity decreases between the carbon and heteroatoms increases. Orientation of polar covalent bonds. If a molecule has two or more covalent bonds, the actual dipole moment of the molecule depend upon the orientation in space. In other words, the actual dipole moment of the molecules is a vector sum of all the individual bond moments. For example, the dipole moment of methylene chloride, chloroform and carbon tetrachloride as shown in the figure. Field effects. We have discussed above the inductive effect operates through bonds. This is another effect which does not operate through bonds but occur directly through space and solvent molecules. This is called field effect. Although it is very difficult to separate inductive effect for field effect, it has been done in a number of cases, generally by taking advantage of facts that field effect depend upon the geometry of the molecules. In inductive effect depend upon the nature of the bond. For example, in isomer 1 and 2, the inductive effect of the chlorine atom of the position of the electron is COH group should be same since the same bond inverse. In other words, acid inductive effect, electromeric effect, is a temporary effect and operates in unsaturated compounds only at the demand of the attacking reagents. It involves complete transfer of pi electron of a multiple bond to one of the bonded atom. Considers, for example, the attack of a nucleophilic to a carbonyl group. In the presence of a nucleophilic, the pi electron of the carbon oxygen double bond are completely transferred to the more electronegative oxygen atom. Here we see the reaction take place. As a result of this reaction, the displacement of positive charge of the carbon atom of carbonyl group increases and the fertilization and attack to the nucleophilic on it. Such a complete transfer of electrons on a multiple bond of to the bonded atoms in the presence of attracting reagents is called electrometric effect, or simply the E effect. Type of electrometric effects. If the pi bond are transferred to that of the double bond to which the attacking reagent gets finally attached, the effect is called positive E effect. For example, addition of acid to alkene. If on the other hand pi electron are transferred to atom or double bond other than the one of which is attacking reagent gets that's finally attached, the effect is called E effect. For example, addition of cyanide ion in the carbonyl group. Significance of electrometric effect. It may be noted that so far it has not been possible to distinguish experimentally between I and E effect, but the fact that the relativity of the molecule increases considerably upon the cloud approaches to the reagent definitely suggested the improvement of some electronic effect on the electrometric effect. In certain molecules, both I and E effect operates together. Sometimes they assist to the reinforces each other, and sometimes they opposes. Therefore, they opposes each other. It is always E effect which dominates over the I effect. Compression and inductance and electromagnetic effect. Inductive effect. It operates only the saturated compounds containing at least one polar sigma bond. On the other hand, in electrometric effect, it occurs in unsaturated compounds containing at least one double or a triple bond which may or may not be a polar in nature. Where inductive effect, it is a permanent effect and involves the mere displacement of sigma electrons. On the other hand, it is temporary effect and involves the cleavage of multiple bond with complete transfer of shear pair of electron to one of the bonded atom. Inductive effect, it does not require any outside attacking reagent for the operation, and it takes place only in the presence of attacking reagents. Fourth point is the displaced electron pair does not leave its molecule's orbital, but due to the inductive effect, there occurs a slight disruption in the shape of the molecular orbital of the polar sigma bond. On the other hand, the electron pair which gets transferred completely during electrometric effect leaves its original molecule's orbital and get transferred to a new molecules. Point number fifth is due to the inductive effect, only a partial separation of positive and negative charge occurs, but its ions are not formed. Due to electrometric effect, these occurs a complete transfer of electrons from the reagents to the separate or vice versa. Hence, ions are always formed. Resonance. The concept of resonance or mesomerism was induced to explain the properties of such molecules which cannot be represented by a single electron structure. In such cases, it has been found that the molecules can be represented by two or more electronic structures, each one of which can explain most but not of the all observed properties of the molecules. The real structure of the molecules lies somewhere in between all three electronic structures, which, however, cannot be represented on paper. Thus, the phenomena of resonance is said to be occur whenever for a molecule we can write two or more Lewis structures which differs in the position of the electrons but not in the relative position of atoms. The various Lewis structures are called contributing or canonical and resonance structures. The actual structure of the molecules is represented by any of the resonance structure, but it is resonance hybridized of all three Lewis structures. The various resonance structures are separately by a double-headed arrow, as we see in the figures. Resonance energy. A resonance hybrid is always more stable than that of conical structures. This stability is due to delocalization of electron and measured in terms of resonance energy or delocalization energy. It is defined as difference in the internal energy of the resonance hybridized or the actual molecules are the most stable conical structure. Further, more the number of equivalent structure, greater the delocalization of electrons. Higher is the resonance energy and hence more stable is the compound. If case of benzene, this resonance energy has been determined to be per mole. The resonance can be calculated either from the heats of hydrogenation of heat of formation. Both these methods are illustrated between below by taking benzene as an example. For from heat of hybridization. Heat of hybridization is the amount of heat evolved when 1 mole of the unsaturated compound is hybridized. When benzene is fully hydrogenated, it gives cyclohexane and 208.636 kilojoule per mole of heat is evolved. On the other hand, cyclohexane having a six-membered ring and one double bond when hydrogenated gives cycloalkane and 119.66 kilojoule per mole of heat is evolved. If this double bond benzene did not interact or therefore it were not resonance, then 3 times of heat hydrogenation of cyclohexane. As we see in the examples, conditions for resonance. The main condition for resonance are the various resonance structures should differ only in the position of electrons and not in the position of nuclei. For example, we see in the figure. The second is all the atoms taking part in resonance must lie in same plane or nearby. So, all conical forms should have the same nuclear or paired and unpaired electrons. For example, CH2 bond CH2 is not a valid conical structure for CH2 double bond CH2. Fourth is all the conical structures should have same nearby the same amount of energy and stability. Such structures are called equivalent structures. For example, we see fourth and fifth examples below. Fifth is, in fact, all the conical structures contributed towards the resonant hybridized in portion of their relative energies and stabilities. The most stable form contributing is most Sixth is the greater the number of significant conical structures that can be written for a molecule and more nearly they are equal in energy, greater is the resonance energy of the molecules. Seventh, while determining the relative stability of different resonating structure, the following points must be kept in mind. Properties of resonance hybridized. First is stability. A resonance hybridized is always more stable than that of its conical structure. The different resonating structure, the following points must be kept in mind. Properties of resonance hybridized. First is stability. A resonance hybridized is always more stable than that of its conical structure. The stability is due to delocalization of electrons as a measured in terms of resonance energy. More of the number of equivalent resonance structure, greater the delocalization of electrons. Larger is the resonance energy and hence more stable is the actual molecules. In other words, larger the resonance energy, more the stable is the compound. Second is bond length. The bond length is in the resonance hybridized or real molecules are different than those of intercontributing structures. For example, all the carbon-carbon bond length is in benzene are equal and 1.39 angstrom, while each of two contribution in the bond length, resonance or mesomeric effect. We have seen above that resonance and mesomerism involves delocalization of pi and n electrons in conjugate system. As a result, this displacement of electron and centers of low and higher electron density are created in such molecules which in turn affected their relativity. The generations of centers of low and high electron density is conjugated system as a result of phenomena of resonance is called resonance effect and mesomerism effect M effect. Type of resonance or mesomeric effect. Depending upon the nature of functional group and adjacent multiples, bond resonance and mesomeric are of two types. First is minus I or minus M effect. Electron withdrawing groups such as carbon double bond, oxygen, minus COR, C triple bond N and minus NO2 etc., which present adjacent to a double bond withdrawing to the electron double bond towards themselves. Such groups which withdraw electrons from double bond as a result resonance RB2 procedure of minus. Second one is positive R or positive M effect. Groups such as oxygen bond hydrogen, oxygen R bond R, S bond R, NH2, NRH, NR2 and halogen with one or more pair of electron which present adjacent to the double bond donates electron to the double bond. Such groups which donate electrons to the double bond though resonance is said to be possesses positive R, as we see in the examples. Difference between resonance and inductive effect. Resonance effect occurs only a conjugate system such as conjugate polymers, alpha, beta, unsaturated carbonyls compounds and aromatic systems. On the other hand, inductive effect occurs in saturated compounds. Second is it involves delocalization of n and pi electrons. On the other hand, displacement of pi electrons. Third is during resonance effect, the electron pair is completely transferred and hence full positive and negative charges appears. But in these effects, it does not involve delocalization of electrons. Fourth is resonance effect are transmitted all over the length of the conjugate system without suffering much charge in magnitude. For example, C3 is positive as C1. During inductive effect, the electron pair is slightly displaced towards the more electronegative atom and hence also partial positive and negative charge appear. And fifth is inductive effect are transmitted only over short distance distance in saturated chains and magnitude to effect increasing rapidly as the distance from the heteroatom increases. This effect almost becomes negligible beyond two carbon atom from heteroatom. Applications of resonance effect: low reactivity of or vinyl or aryl halides. As compared to aryl halides, vinyl and aryl halides are far less reactive towards nucleophilic substitution reaction. This the reason being that due to positive R or positive M effect, the lower pair of electrons or halogen atom are delocalized over the entire pi system. Consequently, vinyl chlorides can be regarded as a resonance hybridized of structures and chlorobenzene as a resonance hybridized structures, as we see in the high reactivity of aryl benzyl halides. Aryl and benzyl halides are far more reactive than primary aryl halides towards nucleophilic substitution reaction. This is due to the reason both aryl and benzyl halides rarely undergo ionization for the resonance stabilizing carbocations. Here we see aryl bromide ionization and then resonance. Third is acidity or carboxylic acids. The acid character of carboxylic acids is due to the release of H positive ions in aqueous solution to form carboxylate ions. Both carboxylic acid and carboxylate ions are stabilized by resonance, whereas conical structures or carboxylate ions are equivalent and carry only a negative charge, but the conical structures of unassociated carboxylic acid are not non-equivalent but is involved separation of charges. Since energy is needed to separate positive and negative charges, therefore carboxylate ion is much more stable than that of carboxylic acid, and it is this greater stability of carboxylate ion as compared to carboxylic acid which is responsible for ionization and hence is acid character or carboxylic character. Relative strength or acidic character of phenols and alcohols. The acid character of phenols and alcohols is due to the release of portion in aqueous solution to the form of phenoxide ions. Comparison of relative basic strength of ethylamine and aniline. Ethylamine is a much stronger base than the aniline. As we know, the ethylamine, the positive I effect of ethyl group increases the electron density on the nitrogen atom nearby the increasing of basicity. As we see in the example, the sixth is comparison of basic strength ethylamine and acetaldehyde. Ethylamine is a much stronger base than that of acetaldehyde. That may be explained as below. In ethylamine, positive I effect of ethyl group increases the electron density on nitrogen atom. As we see, positive I effect of ethyl group increases the electron density of nitrogen atom, therefore nearby increasing its basicity. And on the other positive side, positive R effect of the amino group decreases electron density on the nitrogen atom, therefore nearby increasing its basicity. Effect of the dipole moment. The overall dipole moment of a molecule is the vector sum of the dipole moment of the individual polar bonds present in the molecules. However, resonance may either increases or decreases the magnitude of the overall dipole moment of the molecules depending upon the nature of the polar bond present in it. For example, the dipole moment of ethyl chloride is much higher than that of vinyl chloride. This is due to the reason that vinyl chloride is the inductive effect and resonance effect of chlorine operates in the opposite direction, thereby decreasing its dipole moment as compared to that of ethyl chloride, where only inductive effect operates. For example, tautomerism. It is a special kind of functional isomerism in which the isomers exist a dynamic equilibrium with each other. It arises due to the migration of hydrogen atom from one polyvalent atom to the other within the same molecules, which necessary rearrangement of linkages. The isomers thus obtained is called tautomers and the phenomena is called tautomerism. There are many types of tautomerism, but keto-enol tautomerism is the most important. This is the type of tautomerism. One form consists the keto group and other the enoic group. This is the simplest example of keto-enol tautomerism is acetaldehyde acetone cyclohexane. Factor affecting the relative amount of keto-enol forms keto-enol tautomerism. Stability of enol group formation forms. As starred above the simple aldehydes and ketones, the amount of enoic form is negligible small. However, the enoic form is stabilized by intermolecular hydrogen bonding. For example, similarly, acetone are the X-hybrids, keto-enol tautomerism, but the amount of enoic form here is much higher than even in acetic esters. This is due to the reason that keto group is much bigger, much better electron withdrawing group than that of ester group. The second is steric hindrance. Another factor which determines the enoic constant is the stereo factor. To illustrate this, consider the enoic constant. Although both of the enoic is stabilized by H atom, the enols form the alpha methyl acetylene is the unstable to some of the extent of steric repulsion due to the presence of alpha methyl group. Affective polarity of solvent. Polar porritic solvents such as water, methyl, acetic acid, and which are form H positive bond, while the carbonyl group of keto constant. On the other hand, approximate solvents such as hexane, benzene, etc. increases the enol constant. For example, enol forms acetylene 76% of ethanol and 92% of hexane. Condition in contrast, nitroacetone nucleotautomerism 1 degree and 2 degree nitroalkanes which contains acidic hydrogen show tautomerism. The second is nitroso-oximino system. For example, nitrosoethane and oximino. Amine ename system which is propane 1 imine which is imine and propane 1 in 1 amine is enamine. Amino imido reaction or system. Difference in resonance and tautomerism. Difference resonance structures differs only in the portion of the electron but not in the portion of atoms. But in tautomerism differs both of the position of electrons as well as atoms. Second is the various contribution structures as imaginary and thus the questions are isolation does not arises. Tautomerism actually exists and can even in isolated under suitable conditions. Third is the resonance structures are not in dynamic equilibrium. The tautomer exist in dynamic equilibrium with each other. Fifth is the various resonance structures are separated by double-headed arrow. The tautomers are separated by equilibrium in by these arrows. Aromaticity. What is aromaticity? Benzene and all the compounds which resembles benzene in chemical behavior are called aromatic compounds. These exhibits the properties which are quite different from those type of alphabetic and acyclic compounds. Some important characteristics are of the aromatic resonance theory. Since benzene and other aromatic compounds having high resonance energy, therefore MgS then we defines aromatic compounds as cyclic compounds which are the atom takes parts a single conjugate system and have high resonance energies. Second is aromatic 60 theory. All the compounds which contain a closed loop of 6 electrons were called aromatic and theory are called aromatic 60 theory. Third is Huckel's rule. On the basis of molecular orbitals calculations of physics is pointed out the orders of aromatic a compound must fulfill in these energies. The molecule or ion must be flat or planar or nearby. So second is it should have a cyclic cloud of delocalized pi electrons above the and below the plane of the molecules. Third is the pi electron cloud should also encompass of the carbon atom of the cyclic system. The total number of pi electrons in the molecular species or ions should be 4n plus 2 where n is 1, 2, 3. Application of Huckel's rule. In this light of Huckel's rules, the evidence of the aromatic compounds needed not necessarily contains a benzene ring. All what is required is that the molecules of compound must be planar and should contain acyclic compounds and delocalized pi electrons above and below the plane of the ring. The cyclic conjugate planar molecules containing 2 into n is equal to 0, 6 into n is equal to 1, 10 into n is equal to 2, and so on up to pi. Hydrogen bonding definition. Whenever a molecule contains a hydrogen atom linked in a highly electronegative atom, this atom attacks to the shaped pair of the electrons more of so this end of the molecules becomes slightly negative while the other end becomes slightly positive. The negative end of the molecule attacks to the positive end of the other end result as electrostatic attraction. A weak bond is formed between them. This bond is called hydrogen bond. This is represented by dotted line as shown below. Conditions of hydrogen bonding. In formation of hydrogen bonds, these following conditions are required. The molecule must contain a highly electronegative atom linked off to H atom, and second is the size of the electronegative atom should be small. Strength of hydrogen bond. Hydrogen bond is very weak bond. The strength of hydrogen bond is intermediate between the weak van der Waals forces of and strong covalent bond. As we shown, type of hydrogen bonding. Intermolecular hydrogen bonding. When hydrogen bonding takes place between the different molecules of the same or different compound, it is called intermolecular hydrogen bonding. For example, hydrogen fluorine having the highest value of electronegativity forms the strongest hydrogen bond. Hydrogen fluoride thus exists. Second is water H2O. In water molecules, the highly electronegative oxygen atom is linked to the hydrogen atom because of the higher electronegativity. The oxygen atom attracts the electrons of the OH bonds towards itself. As a result, oxygen carries partial negative charge and hydrogen atom partially positive charge. Intermolecular hydrogen bonding. The hydrogen bonding which takes place with the molecule itself is called intermolecular hydrogen bonding. It occurs in compound containing two groups such that one group contains H atom linked to an electronegative atom and group contain a highly electronegative atom linked to a lesser electronegative atom. The bond is formed between H atom and the group which is electronegative atom to the group. For example, Condition of intermolecular hydrogen bonding. The following condition must be satisfied. First is the molecule should contain two groups, such as one group contains H atom linked to the highly electronegative and other is should be the contain a highly electronegative atom linked to a lesser number of electronegative groups. Second is the molecule should be planar, and third is the hydrogen bonding should lead to the formation of either a 5 and 6 membered ring of including hydrogen atom.